All right. Yesterday we have discussed some of the important aspects of step-by-step procedure for testing assumptions. We have covered up to third assumption uh, of regression, and I have let you know the entire procedure using the Stata. Today we will cover the remaining assumptions, how to check those assumptions, what is the specific detail of these assumptions, how we can provide the remedy, what options do we have if a particular assumption is not fulfilled. So let me open the data and let me open it from here, data MP file. I am using the same data set that I have previously used. I have already shared this file with you. That is cgdata.pda. The same file that I have previously used, I am using it again with the same set of variables like Robbins Q, ROA, and so on. So this was the file that I have used in yesterday's session. So today I am going to discuss the next assumption, that is absence of perfect multicollinearity. First, we need to understand what is multicollinearity and what do we mean by perfect multicollinearity. Multicollinearity means a correlation between independent variables. So when there is a correlation between independent variables, it is known as multicollinearity. Every time when there is a correlation between independent variables, every time it does not mean that it is an issue. It becomes an issue when it is perfect multicollinearity. So what do we mean by perfect multicollinearity? When the value of correlation coefficient is more than 0.80 or plus minus 0.80 with significance p-value. You remember that we have discussed the procedure of calculating the correlation between the variables. I have let you know the correlation procedure. This is the simple command of correlation, but if you would like to know the significance value of your variables or the correlation variables, you can use this option. So let's suppose these are my variables. I would like to see the correlation. PWCORR. I need to put my variable one by one. You simply need to click from here to arrow sign. You just need to click one by one like this. And then you need to put a comma. And what is the remaining part? That is star 0.05 6. You can simply copy it from here and you can put it here like this. Now, you will see a Pearson correlation regression where the first part is basically the correlation coefficient and the second part is the p-value. You can see there is a significance correlation between Tobin's Q and ROA, but this value is less than 0.80. Although it is significant, but it is less than 0.80. What we need to understand that the correlation value should be greater than 0.80 in order to consider it issue. So when the correlation coefficient between two independent variables is greater than 0.80, then it becomes the perfect multicollinearity. Value should be less than 5%. Then it meets the condition. So in our case, this value, these are independent. If they are independent variable, although they are dependent, Dobbin's Q is dependent, RO is dependent, we don't need to see them. We need to see the independent variable with other independent variables. So, for example, institutional ownership is one independent variable, and PRON is another independent variable. So between them, there is a negative correlation, but this value is also less than 0.80. Although it is significant, but this is less than 0.80. So we cannot say that there is multicollinearity here. And both of these are independent variable. They are not dependent variable. Whenever you find a high correlation between independent and dependent variable, that is favorable. That is actually favorable. There should be a high correlation between independent and dependent variable, but there should not be high correlation between two independent variables. So if both are independent variable, there should not be a high correlation. But in this case, it is not perfect correlation. Similarly, you can say here, it might be a potential correlation, perfect correlation value here. FFI with institutional ownership. So we have found a value which is approximately 80%. So our criteria is the value should be greater than 0.80, but this value is very close to 0.80 and it is significant too. So there is a potential multicollinearity between institutional ownership and financial ownership. There is a potential multicollinearity, but in other cases, this is not potential multicollinearity. In the same way, you can see other variables. We cannot find any potential value here. Similarly, this one, there is no any other value. You can find here, yes, there is no any other value to indicate any potential issue of multicollinearity. There is some multicollinearity in case of total asset and firm size. So what we have concluded if we are checking the multicollinearity using Pearson correlation, then we need to see whether the correlation coefficient is 0.70 and the p value should be less than 5% in case of perfect multicollinearity. So perfect multicollinearity should not be there. If your data proves perfect multicollinearity, it means your assumption is violated. There should be no perfect multicollinearity in your data. So linearity related can cause problem in estimating the regression coefficient, and important assumptions for the multiple regression model is that independent variables are not perfectly multicollinear. So what are the other procedures? One regressor should not be linear function of another. Regressor means independent variable. So your independent variable should not impact other independent variables significantly. So when multicollinearity is present, standard error may be inflated. What do we mean by standard error? I need to show you the standard error. This is the output table I was using yesterday, and I have run a regression like this. Now, this is basically the standard error. What will happen if standard error inflated? I have told you that your t value is calculated on the basis of coefficient divided by standard error. So if we increase the value of standard error, what will happen to the t value? The t value will decrease. It means this value remains same, but this value increase. So this value divided by this value will decrease the t value. So it means sometimes a variable may be significant, but due to multicollinearity, it becomes insignificant because the standard error might have inflated. So what we have concluded here, we have concluded here that multicollinearity, if present in your data, it will increase the standard error. It will inflate the standard error. So Stata will drop one of the variable to avoid a division by zero in the OLS procedure. So whenever you are going to apply OLS model, and if there is a heavy multicollinearity in your data, it will automatically drop the variable causing the multicollinearity. And this is basically suggested by Stoke and Watson 2003 in their book in chapter number 5. So, how multicollinearity occurs? What are basically the sources through which multicollinearity arise in your data? When there are a large number of independent variables with low degree of freedom, it means your model is over determined. It means you have included some unnecessary independent variables in your model. Always remember that including independent variable in your model requires the theoretical backing, the literature backing. So always include only those independent variable in your model which are theoretically correct, which provide the justification in literature, which provide the justification in some theory. So you need to include only sufficient number of independent variables. If you include some insufficient number of independent variable, it will over determine the model, and it will also decrease your degree of freedom, because every time you include an independent variable in your model, it will decrease the degree of freedom. So by decreasing the degree of freedom, your f value will decrease, and it will ultimately decrease the statistical fitness of the model. So always remember that you need to have sufficient number of independent variables. The second thing is common trend of independent variables. Sometimes you are using the time series data and you find some common trends in independent variables. So what do we mean by common trend? Common trend means if one variable is increasing, other may also be increasing. The third one may also be increasing. So they are providing a common trend in independent variable. In that case, multicollinearity may be there. So if one independent variable is increasing, other is also increasing, it means they are providing some common trends. Then there might be some issue of model misspecification. Sometimes you include a large number of independent variables, and sometimes you omit some important variables. Sometimes you do not include some sufficient number of variables. Adnan Afzal asked how much IVs should be in model to avoid this problem of over determination. Basically, there are some tests which would let you know uh, regarding the model specification. I will let you know. Um, there should be number of variables in your model which would not create the issue of multicollinearity. So if multicollinearity is not there and your R square is good, it means your model is okay. So there is no predefined number about the inclusion of independent variables. The only criteria is that the inclusion of independent variable should not create multicollinearity. So if multicollinearity is there, you need to drop some of your variable, a particular variable or some of your variable from your model to make it perfect. So there is no limit regarding how much independent variable we can provide in the model. The only criteria is that you need to test the specification, you need to check the R square value, you need to check the multicollinearity. Correct. Next is inclusion of some relevant independent variable in the model, including import along with export may cause multicollinearity. Some of the variable may be impacting each other, like you have included import and export variable, and they are basically impacting each other. So in that case, there might be a chance of multicollinearity. I have seen a data set today. Someone has contacted me that she is facing an issue of multicollinearity in their data, and I noticed that she has data on ROA as well as on ROE. Both are basically the indicators of firm performance. So she has included both of them, and both of them are heavily impacting each other. So, due to the inclusion of both of those variables, multicollinearity was there. So, I suggested her to drop one of them. Either she need to drop one of them, or she need to create an index, a common index where both of them would be considered. So when your two variables are relevant to each other, it may cause the multicollinearity. Then there are some theoretical consequences that would happen when multicollinearity is there. A larger sample is needed. If you want to control the multicollinearity issue, you need to increase your sample, because the multicollinearity issue is a sample issue. If your sample is small, there is a high chance of multicollinearity. And if you want to control the multicollinearity, you need to increase your sample. So if present data contains smaller sample, however, in some cases, the sample cannot be enhanced due to time and cost constraints. So sometimes your data cannot be increased. In that case, we need to change our model. We need to change the estimation methods. But the best method to control the multicollinearity issue theoretically, to increase the sample size, because with the increase of the sample size, this issue is resolved. But if you cannot increase the sample size, you can change your method of estimation. You can control the variable having the multicollinearity issue by dropping it, or by converting it into some other measures. Then it is a sample phenomena, not in the case of entire population. So you can still run your estimates, because it only involves in the sample. It is not considered in the entire population. So usually found in a non-experimental data like GDP data, its determinants. So it is a data deficiency problem. It means if you increase the sample size, it will automatically resolve the multicollinearity issue. So a simple interpretation of the coefficient may not be valid. The interpretation of the coefficient may change if there is a multicollinearity issue with your data. Either you need to resolve the multicollinearity issue. If you cannot resolve the multicollinearity issue due to your limited sample, then you need to be very careful in the interpretation of your coefficient, because the simple interpretation cannot be valid. So we need to provide special interpretation in case of multicollinearity exists, and we cannot eliminate it due to any constraint. So OLS estimator remain unbiased, no violation of the blue property. So blue stand for best linear unbiased estimator. You can still estimate your model if multicollinearity is there, but you need to be very careful regarding the interpretation of the coefficient. Now, what are the practical consequences? What if your model contains multicollinearity? What will be the practical implications of that model? Uh, your signs of the coefficient may be wrong. You are expecting positive signs, and the estimation shows you negative signs. Your theory says a positive relationship between different variables, and you are basically facing with opposite signs or with opposite relationships. So there might be wrong signs of coefficient in case of multicollinearity. There might be low t values but high r values. R values might be high, but the t values are low. This is basically the indication of multicollinearity. If multicollinearity exists in your data, your R square would be high, but your t values would be low. So always remember, when the R square is high, the t values should be significant in order to validate your model. But if you face the reverse situation where R square value is very high, but T values are low or insignificant, it means multicollinearity might be there in your model. That is basically uh, th- that is basically a sign that you can assess that there might be multicollinearity in your data. Low t values due to high standard errors of coefficient. This is the point we have already discussed, that standard error might be inflated. Due to inflation of standard error, your t value will decrease. The model may be unstable. You can detect the stability of the
Assalamualaikum.
model. Yes, yes, Dhananand sir.
आपकी आवाज जो है ना वो ऑफ हो जाती है, योर वॉइस गोज ऑफ.
Uh, uh, can you hear me clearly, Dhananand sir? Is it audible now? Hello, is it audible? Vakas, can you hear
Right now
me?
it's
Is it? Please indicate. Is it audible now? All right. So I was discussing that your model may be unstable. It is not statistically stable model, and you can detect the stability of your model using Pollen method. I will let you know how to apply the Pollen method using Stata. And the next procedure is basically individual variable were not significant, but the model seemed to be statistically fit. You need to check why whether your model is statistically fit, but your individual variable are not significant. This may be another cause of multicollinearity. So how you can detect the multicollinearity? There are two methods. One is BIF method. One is basically the correlation method that I have previously discussed. You can see the correlation metrics of your data, from where you can find out whether there is a multicollinearity between the variables or not. The second method is basically the VIF method, that is variance inflation factor method. The third method is pollen method. Pollen method is basically used in order to see whether due to multicollinearity your model is stable or not. So it will indicate that your model is statistically stable or not due to multicollinearity. And it will also let you know the multicollinearity in your model. So pollen method basically perform both functions, multicollinearity detection as well as uh, the stability of your model. So detection of multicollinearity, how we can detect multicollinearity using VIF method. In case of VIF method, you need to consider this command first. That is regression command. So let's apply using our data, which is provided here. X are dependent variable like Tobin's Q, then our independent variable one by one, like this. Press enter. It will run the regression. Now, first we need to see our model is statistically fit. Our R square is normal, and you see a couple of variables are significant, and some of the variables are not significant here. You can see, you can observe here. You can run this command with robust, like I have told you yesterday, that robust is used basically to control heteroscedasticity. So you need to control the heteroscedasticity in order to see the true t value. This is the true t value. Now I need to see whether there is a multicollinearity issue in my data or not. So I need to write simply VIF. which is variance inflation factor. So when I run the VIF, you find two columns. One is with VIF and one is basically the 1 divided by VIF. The second is called the tolerance. So in case of VIF, the value should be less than 5. If the value for each individual variable is less than 5, so it means that you can ignore the multicollinearity. There is a multicollinearity, but it is ignorable. It is mild multicollinearity. And if the VIF value for each individual variable or for a specific individual variable is greater than 5, then there is an issue and you need to drop that variable. So this is the criteria which you can use here. I have provided a table. Uh, a perfect multicollinearity is when VIF value is greater than or equal to 10. And 1 divided VIF is less than 0.10. So it is a problematic multicollinearity, and you need to drop that particular variable that is showing either this value or this value. But when your multicollinearity is between 5 to 10, it means it should be less than 10. Then it is called moderate or mild multicollinearity. It is ignorable. And if it is less than 5, it indicates no multicollinearity. And it is the best one that should be ignored. So in our case, these are basically the ignorable because these are less than 5. So you need to consider a VIF value that should be less than 10. So this is the VIF criteria. In our case, there is no multicollinearity here. But in case if you find a multicollinearity issue in a particular variable, for example, let's suppose institutional ownership shows a multicollinearity of 10, then we can consider it to delete from our data set, and we can run the regression without that particular variable. So that is the remedy that you can consider here. So the next method is colon method. Colon method is used to provide two functions. One function is basically it provides you the multicollinearity, whether there is a multicollinearity in your data or not. And the second function for considering the colon method is basically to provide you whether your model is stable or not. So let's introduce another command on collinearity, the colon command. The colon command display several different measures of collinearity. For example, we can test for collinearity among the variables we have used in two examples above. Note that colon command does not need to be run in connection with regression. In case of VIF, you need to run the regression first. Then you can consider the VIF. But in case of colon command, you don't need to run the regression. Unlike the VIF command, which follows a regression command, also note that only predictor independent variables are used with colon command. So what you need to do, you need to write colon and you just need to write the independent variable. So let's consider it COLLIN, and you need to provide only the independent variables like this. These are my independent variables. You don't need to use the dependent variable in your model. And click enter. Command colon is unrecognized. They have not recognized it. Uh, SSC. Whenever there is an absence of a command, try to search it from here. Like I need to see whether they have applied this command or not. So they have provided me two options. How to run this procedure. I need to get this from this particular website. Whenever a new command applies uh, in your Stata, it need to be installed. So first I will let you know how to install a command. Because this command was not recognized with this version of Stata, so I simply write ssc install and the name of the command I was running. So whenever you run a command and it is not recognized by the Stata, you just need to write ssc install and the name of the particular command that is not recognized by the Stata, and it will give you some options. For example, in search option, I go to this, and they have provided me different links from where I can find this software or this command. So I just click the first one, and it give me option click here to install. I just click over it, and it is going to install the colon command. It is basically not available in the previous versions of the Stata. It is provided in the latest version, but you need to you can simply install this command if you are using the previous version of the Stata using the same procedure I have done here. So colon command has been installed. So what I need to do, I need to run this command again. I just need to copy the command from here like this and click enter. Command calling is unrecognized. Why this is unrecognized? You can find the correct procedure help. Whenever it is giving some error, you can still find how to run this command. There are basically the sources where this command is provided, and you need to find out the correct one. You need to see which one of these is basically considering the colon. Yes, this one is basically relevant to colon. So you need to search out which one is mentioning the colon command. So click on it. Previously, I have not checked whether the source provides the colon command. Now this time it provides the colon command. Click here to install. Now it is installing. Click here to go to the previous window. Click here to go to the previous window and cross it. Now it might be installed. I hope it will run this time. Now it is run. Now you can see it is run because it is installed now. So in colon diagnostic, you are seeing the VIF value again, and you are also seeing the tolerance value, and you are seeing the R square here. So they have provided a lot of values here, and they have also provided the eigen's value here and the continuous index value here. And you can also see here some value as a correlation matrix or condition number index. So how can we interpret whether our model is stable or not? So the condition number the condition number is commonly used as an index of global instability of the regression coefficient. A large condition number with 10 or more is an indication of instability. So we need to see the condition number. This is condition number, and this is more than 10. So it indicates that our model is unstable. So at present, this model is not stable. There are a lot of values which are creating issues with this model. So we need to understand that the combination of these uh, uh, variables uh, cannot be good for our model. So how can we understand that which combination are good? If we run regression on the basis of this variable, this will indicate uh, VIF like this, sorry, like this, and it will indicate an R square of this value. If we consider only institutional investor, it will indicate a VIF value like this, and it will indicate a R square value like this. So you need to understand which one of these showing the lesser amount of R square value. Like S growth has very less amount of impact of the R square. Leverage has some 17% impact. uh, FH has only 9% impact. So if I run regression with institutional ownership like Rex Robbins Q with institutional ownership like this. So I will see what will be the R square value. The R square is basically only 0.003. So it indicates that this is not a good value. So it is impacting R square approximately 74%. So it means if R square is higher in these cases, you should avoid those values or those independent variables. So in this case, uh, the institutional ownership is not perfectly explaining Tobin's view. If I run the regression on ROA with the same independent variable, so let's see what will happen. Click enter, and it's still showing a minimum amount of R square. The model is fit, but the R square is very low with this model. Although there is a weak impact here, and you can also find there is no impact here. So let's see what will happen if we try a value with minimum R square here, like escrow. Post rec Robin's Q and escrow. Escrow has the minimum amount of R square here, but what will happen if we regress here? So it shows zero R square, and it shows that model is not stable. So you can find here the values. You can try different combinations, but it is proved that your model is not stable here. We need to address other issues in our model, like we need to check uh, whether our data is normal, whether there is uh, absence of some important variable in the model. So there is less than 1 minute. If the meeting ends, please join using the same link that you have used for joining this meeting. Join again using